Welcome back to the channel. Today we're diving deep, literally, into the world of continuous flight auger piles, or CFA piles, for those of us who don't have time to say 5 syllables. Think of this as your master class in going from blueprint to bedrock. And yes, I did just make a dad joke about foundation work. Buckle up, engineers and infrastructure nerds. This is about to get technical and entertaining. So why would anyone choose CFA piles over other foundation methods? Well, imagine you're building in soil that's basically oatmeal consistency. Soft, unstable, waterlogged. Fun times, right? CFA piles absolutely thrive in these nightmare conditions. Plus, they're the quiet neighbors of the pile world. Low noise, low vibration, which means you won't wake up every building in a 3-block radius like you would with driven piles. And speed? We're talking 15 minutes or less per pile. That's faster than most people can decide what to order for lunch. Now, historically, CFA piles had one Achilles heel: quality control. Engineers would get nervous because, unlike cast-in-place piles where you can see everything happening, CFA work happens underground. It's like trusting someone to assemble IKEA furniture in the dark. But here's the game changer: modern automated monitoring systems. These bad boys track every rotation, every pump stroke, every millimeter of depth. Quality control concerns? Consider them obliterated. All right, let's break down how these things actually work. It's a 3-phase process, and honestly, it's kind of elegant when you think about it. Phase 1, drilling. We've got this hollow stem continuous flight auger, basically a giant screw, that drills down to our target depth. The soil stays in the flights as we go, which is brilliant because it provides lateral support to the hole. No cave-ins, no drama. Phase 2, grouting. Now here's where it gets spicy. As we pull that auger back out, we're simultaneously pumping grout, or concrete, through the hollow stem under serious pressure. We're talking 150 to 250 psi. This fills the void from bottom to top, and that pressure is what keeps the hole from collapsing. It's like doing a magic trick where you pull the tablecloth but leave all the dishes standing. Phase 3, reinforcement. While that concrete is still fluid, we immediately drop in a steel rebar cage. Timing is everything here, folks. You snooze, you lose. Or in this case, you get a pile without proper reinforcement, which is decidedly not good. Before we even think about firing up a drill rig, we need to do our homework. And I'm talking serious homework. Not the kind you copy from your friend 5 minutes before class. First up, geotechnical investigation. This is literally the bedrock of your design. See what I did there? We need soil stratification, groundwater depth, bearing capacity, and, hey, let's make sure there aren't any surprise boulders or forgotten concrete chunks waiting to ruin our day. Second, structural requirements. Review those design documents like your career depends on it, because it does. Pile depth, diameter, spacing, load capacity, connection details. Miss one of these, and you're going to have a bad time. Third, regulatory and safety compliance. Get your permits, develop a job hazard analysis, make sure everyone's trained. This isn't optional, people. And finally, material and logistics planning. Make sure you've got quality-controlled concrete and a reliable delivery schedule. Because starting a pile without enough concrete to finish it, that's not just embarrassing, it's a structural integrity nightmare. And nobody wants to explain that to the engineer of record. Time to get our engineering hats on. The axial capacity of a pile comes from two sources: side shear resistance and end bearing resistance. Think of it like this. The sides of the pile are hugging the soil along its entire length, and the bottom is sitting on the ground like a stool leg. For cohesive soils, that's clay for the non-geotechs in the audience, we use the alpha method. Side shear equals alpha times the undrained shear strength. That alpha factor is basically a reality check, because theory and practice don't always hold hands. For cohesionless soils, sands, we use the beta method. Side shear equals beta times the vertical effective stress. Beta is depth dependent because pressure increases as you go deeper. Physics. It's not just a good idea, it's the law. But here's the critical caveat that should be tattooed on every structural engineer's arm. All these calculations are estimates. You validate them with load tests on a project-specific basis. Don't just trust the math. Trust the math plus the field data. Now, here's where things get interesting. You might think, hey, if one pile can hold X amount of load, then 9 piles can hold 9 times X, right? Wrong. Welcome to pile group efficiency, where 1 plus 1 doesn't always equal 2. When piles are close together, they interact with each other, and the soil between them gets stressed from multiple directions. Per AASHTO, that's the American Association of State Highway and Transportation Officials, aka the people who write the rules, pile group efficiency can be as low as 0.65 when piles are spaced at 2.5 times their diameter. You need spacing of at least 6 diameters to hit that magical 1.0 efficiency. And lateral loads? We're talking about forces pushing sideways on the pile, like from earth pressure or seismic loads. This requires the PY method, modeling the pile as a beam on an elastic foundation. The analysis tells us about deflection and bending moments, which dictates how much steel reinforcement we need. This is where the structural and geotechnical worlds collide in a beautiful, nerdy symphony. Let's talk toys. I mean, construction equipment. Not all drilling rigs are created equal, and matching the rig to your project requirements is crucial. First, we've got crane-mounted rigs. These are your mobile, flexible workhorses, common in U.S. commercial work. Torque capacities range from 20 to 120 kilonewton meters. They're great for most applications and can move around the site easily. Then we have the hydraulic fixed-mast beasts. These things bring serious torque and downward crowd force. If you're dealing with larger piles, difficult ground, or those fancy drilled displacement piles, this is your machine. Plus, they're perfect for computer monitoring because everything's hydraulically controlled and sensor-ready. And the augers themselves? You've got soil augers for soft conditions, rock augers for when geology hates you, and specialized drilled displacement augers like Omega or DeWalt systems that actually push soil sideways instead of removing it. It's like the difference between digging a hole and just making space for yourself. Pretty clever engineering. All right, let's talk about actually drilling these things, because this is where art meets science. The key is controlled penetration rate. The auger needs to advance at just the right speed to keep the flights full of soil. That soil is your friend. It's providing lateral support to keep the borehole from collapsing. Now, the cardinal sin of CFA pile installation: mining. This is when you spin the auger too much without enough downward penetration. It's like using an electric mixer on high when you should be on medium. You're just churning butter at that point, not making progress. Mining removes the lateral support, loosens the surrounding soil, can cause subsidence, and leads to massive overruns and grout consumption. Your project manager will not be happy. The solution? Automated monitoring. Modern systems track torque, crowd force, rotation rate, and penetration rate in real time. The operator gets immediate feedback and can adjust on the fly. It's like having a co-pilot who's really good at math and never sleeps. Pro tip from the field: don't start drilling a pile until you have enough concrete on site to finish it. This seems obvious, but you'd be amazed how often this gets overlooked. Cold joints are forever, people.
Phase 2 of the installation process is where things get really critical. This is grouting, and it needs to be continuous and pressurized, kind of like a really important coffee delivery system, except instead of caffeine, we're delivering structural integrity. Step 1. Continuous positive pressure. As the auger comes out, grout is pumped under pressure through the hollow stem. This pressure is what replaces the lateral support that the auger was providing. Stop the pressure, and physics will gleefully collapse your borehole. Step 2. Controlled withdrawal rate. The speed you pull out the auger must be synchronized with the volume of grout being pumped. We're targeting what's called a grout factor, typically 115 to 120% of the theoretical pile volume. That extra bit accounts for soil irregularities and ensures we have a complete, defect-free shaft. Step 3. Immediate reinforcement. That rebar cage needs to go into the grout while it's still fluid. We're talking immediate, like drop everything and do this now immediate. Once that concrete starts setting, your window closes and you're left with a pile that doesn't meet structural requirements. Time is not your friend here. Let's talk about what we're actually pumping down there, because not all concrete is created equal for CFA piles. You've got two main options: sand cement grout or pea gravel concrete. Sand cement grout is like the premium option: high workability, easy to pump, and rebar insertion is a breeze. The downside? Higher cost per cubic yard, slightly lower elastic modulus, and it can degrade faster in sulfate-rich environments. So basically, it's the fancy sports car of pile materials. Performs great, but needs some special care. Pea gravel concrete is your workhorse. Lower cost, more stable in very soft soils, and less prone to volume overruns because the aggregate provides better internal structure. But you need pumps that can handle aggregate, and workability needs careful management. It's the pickup truck, reliable, economical, but not as smooth. Critical spec for both: high fluidity. For concrete, we're targeting an 8-inch slump. That's practically self-leveling. For grout, a flow cone test should give us 10 to 25 seconds efflux time. If your mix isn't flowing like lava, it's not flowing enough. Here's where we talk about making sure everything we just did actually works. Quality assurance isn't a single event. It's a process, a philosophy, a way of life. Okay, maybe that's a bit dramatic, but it is critical. Modern CFA construction has shifted to performance-based specifications. This means we focus on verifying the final product through testing, supported by rigorous process control during installation. The contractor is responsible for achieving the specified performance, not just following steps in a recipe. The inspector's role? Verify the contractor's quality control practices, review automated monitoring data, document visual observations, and witness testing. They're not there to do the contractor's job. They're there to verify it's being done correctly.
And submittals? These are non-negotiable. Pre-construction review of contractor experience, design calculations, detailed pile installation plans, material mix designs. All of it gets reviewed before a single drill bit touches soil. An ounce of prevention here is worth a pound of emergency redesign later. Let's talk about the technology that makes modern CFA piles possible. Automated monitoring systems. This is where we replace guesswork with data, and it's glorious. During the drilling phase, we're measuring depth, auger rotation speed, penetration rate, torque, and crowd force. Every second, these parameters are recorded. During grouting, we track depth, grout pressure, and, critically, grout volume, measured by an inline magnetic flow meter. We don't trust pump stroke counting because pumps can slip. We measure the actual flow. The output is a real-time display for the operator. They can see immediately if something's off and adjust. And after the pile is complete, we have a permanent digital record, a complete autobiography of that pile from birth to completion. The system calculates the grout factor for every increment of depth, verifying shaft integrity continuously. It's like having an MRI of your pile as it's being built. This is the technology that turned CFA piles from maybe a bit risky to industry standard for difficult conditions. Data doesn't lie, folks. Even with all that monitoring, we still need to verify the in-place performance. Trust, but verify. That's the engineer's motto. Integrity testing uses low-strain methods like sonic echo or pulse echo. We perform this on a high percentage of production piles, sometimes every single one. It identifies major defects, voids, discontinuities, significant changes in cross-section. Think of it as an ultrasound for your pile. It's quick, non-destructive, and incredibly informative. Load testing is the big leagues. This confirms the pile's geotechnical capacity actually meets or exceeds design requirements. We do pre-production static load tests on dedicated test piles to validate design assumptions before production starts. Then we do verification tests, rapid or dynamic load tests on a percentage of production piles to confirm consistent performance. This is where theory meets reality, and reality has the final say. You can have all the fancy calculations you want, but until you actually load that pile and measure its response, you're still making educated guesses. Testing turns guesses into certainty. Let's wrap this up with the hallmarks of a successful CFA pile project. These are the non-negotiables that separate amateur hour from professional excellence. First, rigorous upfront planning. Comprehensive geotechnical data and sound engineering design are your foundation, literally. Cut corners here, and you'll pay for it later with change orders and sleepless nights. Second, matched and monitored equipment. Select the right rig for your soil conditions and leverage automated monitoring to control the installation process. Wrong equipment plus no data equals disaster. Third, disciplined installation protocol. Maintain strict control over penetration rate to prevent mining.
Manage auger withdrawal and grout pressure to ensure a continuous pile. This is where craftsmanship matters. Fourth, data-driven quality assurance. Use those digital records as your primary QA tool. They don't forget, they don't exaggerate, and they provide legal documentation if things get spicy later. And finally, unquestionable verification. A mandatory program of integrity and load testing provides ultimate proof of performance. This isn't optional. This is your professional insurance policy. Building the future on solid foundations. That's not just a catchy phrase. It's literally what we do with CFA piles. With modern design, execution, and verification, CFA piles offer a proven, high-performance, deep foundation solution for the most demanding infrastructure projects. They work in terrible soil conditions, they're fast, they're relatively quiet, and with today's technology, quality control is no longer a concern. It's a guarantee. So the next time you drive across a bridge, past a high-rise, or through a tunnel, remember, there's a good chance CFA piles are down there, silently doing the hard work of holding everything up. And now you know exactly how they got there. Thanks for watching. Until next time, keep building, keep learning, and remember, the best projects are built from the ground up.